Welcome to Naradar Academy. In this video, we are going to discuss three important theorems about limit points. Okay, so this video is about only theorems. The first theorem is Bolzano-Weierstrass theorem. This theorem states every infinite bounded set of real numbers has a limit point. Okay, so the set should be what? Infinite, and it should be bounded. If both these conditions are satisfied for any subset of real numbers, then that set will definitely has a limit point. See, already I have uploaded one video for limit points. In that video, I have explained how to find limit points for any subset of the set of real numbers. Okay, so there you can see so many examples for sets having no limit point, finite number of limit points, and infinite number of limit points. So if you go through the video, you can understand better about limit points. So this theorem states if you have an infinite bounded subset of real numbers, that will have definitely a limit point. So for that, I am taking S to be an infinite bounded subset of R. Okay, so bounded means what? It will have upper bound and lower bound. That is, the set is both bounded below and bounded above. So bounded below means definitely it will have infimum. Okay, and bounded above means it will definitely have a supremum. And I am taking K as the infimum for the set and K dash as the supremum. This I am writing by order completeness property of R. What do you mean by order completeness property? That is, if you have any bounded set of real numbers, that will definitely has a supremum and infimum. Okay, so by using that property, since S is bounded, it will definitely has a supremum and infimum, and I am taking them as K as the infimum and K dash as the supremum. So what do you mean by infimum and supremum? That is, for every x belongs to the set S, x is always greater than or equal to k and less than or equal to k dash, because these are the infimum and supremum, no? So all the values will be lying between k and k dash. So in the real line, I can represent like this. Let this be the real line, and what I am saying here, all the elements are greater than or equal to k. So in real line, greater than or equal to k means what? Lying on the right side of k, and less than or equal to k dash means lying on the left side of k dash. Because if you move on the real line towards right side, then the values will be increasing. If you move towards the left side, the values will be decreasing, isn't it? So from this relation, what should I conclude? All the elements of the set S are lying between this k and k dash. So the elements of S will be within this interval only. Okay, this S may be union of intervals or maybe a single interval. Okay, it may be like anything, but it is infinite and bounded. So these are the given conditions for me. So S is lying somewhere in between these 2 points. Okay, right. So now I am defining a new set H as a subset of R. Okay, H contains set of all x belong to R such that x greater than or equal to S only for a finite number of S belongs to S. That means an element belongs to the set H. Okay, a real number belongs to H if and only if x exceeds only a finite number of members of S. That means, see, if you look at this real line, my H is consisting of all the elements left hand side to k, because all the elements of the set of my set are greater than or equal to k, no? So these elements are not exceeded by any element of capital S. Okay, that is, my elements of capital S are what? Not exceeding. So that means the points which are on the left hand side to k will be in H, and k will also be in H, because k is the what greatest lower bound, no? It will belongs to H. So it is a non-empty set, and all these elements on the left hand side will be there. Maybe some of the elements inside this interval may be in H or may not be in H, but as of now my H is non-empty. Okay, also it is bounded above by k dash, because by the definition of H, what do we conclude? It is bounded above by k dash. So k dash is also an upper bound. So but it is an upper bound means by order completeness property of the real numbers, H will have a supremum, no? I am taking that supremum as P. Okay, it is in the previous step I am just telling you k dash is an upper bound, it need not be the supremum. It may be or may not be the supremum. Okay, so I am taking p as the supremum for my set h. Okay, that means what? If you take p is the supremum means if you take any number less than p, it will not be an upper bound. Supremum means least upper bound only, no? Least upper bound means what? It is the smallest upper bound. If you go below that number, it will not be an upper bound. So, if you take p minus epsilon, it will not be an upper bound for h. That means there exists at least one x belongs to the set h which exceeds p minus epsilon. Okay, now x belong to h implies x exceeds only a finite number of elements. But x is greater than p minus epsilon, no? X is exceeding only finite number of elements of S. So obviously p minus epsilon also exceeds only a finite number of elements of S. Therefore, okay, this p minus epsilon belongs to H. Also, one more point we have, since p is the supremum, p plus epsilon cannot be an element of H. Okay, that means what? P plus epsilon exceeds infinitely many elements of S, isn't it? So, but previously what do we say? That is p minus epsilon exceeds only a finite number, but p plus epsilon exceeds infinitely many. That means in between this p minus epsilon to p plus epsilon, this open interval contains infinitely many members of S. Okay, that means what? P is a limit point of S. Okay, so what do we conclude? Yes, the set has a limit point. So we have taken an infinite bounded subset S. Okay, and we have concluded that has a limit point. Okay, I hope you understand this. Next, let's go to the next theorem. The next theorem is a set S is closed in R if and only if it contains all its limit points. That is, S is closed if and only if S dash is what? Derived set. Derived set means what? The set of all limit points of S is a subset of S itself. So, a set is closed means it contains all its limit points. Now, let's see the proof. Already we have a definition for a closed set in R. A set in R is said to be closed if R minus S, that is the complement is open. So if S is closed, if and only if its complement is open. If and only if. What do you mean by open set? A set is said to be open if it is a neighborhood of each of its points. So R minus S is a neighborhood for each of its points. That means what? For every point P belong to R minus S, okay, there exists a neighborhood N which is completely contained in R minus S, isn't it? So for every neighbor, there exists at least one neighborhood satisfying this. So that means what? Whatever point P you take in R minus S, N minus S is, N intersection S is non-empty. Okay, that means no point of R minus S is a limit point of S. Okay, that means every limit point of S is a point of S. Therefore, what do we conclude? S dash is contained in S. Okay, so a set is closed if and only if what? It contains all its limit points. Then next one theorem, a point P is a limit point of the set S if and only if every neighborhood of P contains infinitely many points of S. See, already we have seen the definition of limit point in the previous video. The definition for a limit point is every neighborhood contains a point of S other than P. If it contains at least one point other than P, that is enough for being a limit point. But here what do we say? It is a limit point if and only if every neighborhood contains infinitely many points. So let's see the proof. So one part of the proof is trivial. That is, if every neighborhood contains infinitely many points, that will become a limit point. Okay. So the only part we have to prove is, if it is a limit point, we have to prove what? Every neighborhood contains infinitely many points. Suppose, as a contradiction, let me take, I have a set, okay, and there exists a neighborhood N of P which contains finitely many points, P1, P2, etc. up to Pn, different from P. So what happened in this case? So look at this diagram. See, this is my real line and this P is a limit point, and N intersection S is equal to only this finite number of points P1, P2, P3. I have randomly plotted the points in the real line. Now let me define epsilon I be the distance between P and Pi, okay, and choose epsilon equal to minimum of the epsilon 1, epsilon 2, etc. epsilon n, and define m to be equal to n intersection this P minus epsilon to P plus epsilon. Then this m will also be a neighborhood for P and which does not contain any point of S other than P, because Among the distances I have chosen the minimum distance, no, so definitely that interval will not contain any other point. That means what, I have found out one neighborhood for P which does not contain any point of S. That means what, P is not a limit point. This is a contradiction, no? So this proves, so if a point is a limit point, then every neighborhood contains infinitely many points of the set. Okay, then next, very few results for derived set. A derived set of empty set is equal to empty set if S is a subset of T, then S dash is a subset of T dash, and S union T the whole dash equal to S dash union T dash, and if X belong to S dash, then X belong to S minus X whole dash. Okay, that's all. Thank you.